Well, thank you everyone for the welcome. Happy to be here. As I said, I'm Josie Peacock. I've been dealing with industrial automation in one form or another for nearly 25 years. And it's, yes, I started when I was 20 years old. I'm not that old. But anyways, in today's world, you're starting to hear you've heard of the IoT, Internet of Things, and now you're also starting to hear the industrial Internet of Things, which a lot of industries are interested in bringing their data from the shop floor into their business systems and everything, and Python has a lot of strength in doing that. So you can see the presentation I put up here mainly so I can keep myself focused. We're going to do not talk a lot about Python, but talk a lot about industrial automation, and then we're going to connect Python to the industrial automation and some of the things that you're going to see when you start to work in this world or move into this world. Anybody here has ever dealt with industrial automation or real-time controllers or anything like that? Kinda, sorta. Okay. So that makes me feel a little better because I tried to make this really dumb. So, industrial automation uses specialized hardware that is focused on machine safety and control, and that's one of the things you need to pay attention to. And I'm probably going to repeat myself a lot on the safety thing, but these machines can kill people. And you, with Python, can control these machines directly. So, pay attention. Hardware is usually PLC, PAC, FPGA, or DCS. Anybody know what these acronyms mean? There we go, we got one, two. Okay, first PLC. Now, what's a PAC? It's what the industry wants to start calling their PLCs because PLCs have gotten a lot smarter. They call them programmable automation controllers, and you'll find that you're writing in ladder logics and suddenly you're doing math on a ladder, which is really crazy, which we'll get into ladders here really short and sweet. Usually proprietary operating systems, so this means that, you know, I'm sorry, but they haven't really caught up to the Apple Linux thing yet. We're still very much in a Windows world for the most part. Some of them are still on XP. I actually know one in Scotland that's running on Windows 98, so. And these are real-time processing, as we said, which means that they have to have a delay and an OS delay, operating system delay, of, what is it, tenths or seconds or shorter in increment time, which you look at the specs on some of these things. Basically, they need to make a decision. When something in the real world happens, it needs to react to it. It doesn't have time it just doesn't have time to do the things that your normal PC will do, which for us it happens quick, but for in the real world it's, yeah, we'll talk about that too. And we also spoke about how they're dangerous, so be careful. And talk a little bit about the dangers. Basically, you can pass that off onto the machine tool designer and make sure that machine tool designer understands what they're doing and make sure that you're not liable for stuff. And if you stay more focused on the data acquisition, then it's going to be a little bit easier. But if they want to go into like a web HMI or something, which they have a lot of things like that, which HMI is human machine interface for the tech talk people, or for the industry talk people. And there's a lot of places out there which I've actually looked at prices for using somebody's software they developed, and they charged per tag, which started to get really expensive. It's basically you had an idea of you can read 5 or 6 tags, which is usually a 16-bit word, which we'll get into that too. Now, everybody know what this is? This is a relay. Thank you. Now, why am I bringing up why this is a relay? Because this is what we're going to see in the antiquities and everything, and this is something you'll have to think industrial machine control was back in the mid to late 60s is when it started. And there were a lot of people that, if you've ever watched any of the old science fiction movies, you'll see the robots that sit there and go click, 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 click. That was honest to goodness computer automation, where you're actually controlling logic and controlling machines and controlling a process through relays. And I've worked on, actually, me personally, I've worked on machines that have bubble boards. Anybody ever heard of a bubble board? It's a torrid little magnets that store memory from like the 1970s. I've worked on things with Mylar tape to load the programs. I've worked on, and I've only worked on one machine that used relay logic, thank goodness, because as soon as one of these things go a little wonky, it goes insane. Thankfully, we've moved up from there. But I wanted to bring this up because what we have here is basically the parts of a relay is a coil. So you're going to see this ancient terminology is going to pop back up in a lot of industrial protocols and how you communicate with things. And this is, just for anybody who's curious, it is a dual pole, dual throw relay, which means you got 2 conductors and 2 throws. Now, I'm going to get there. This is a very common relay start circuit that you're going to see in industry. And has anybody here heard of ladder logic? We're going to do 1 rung of ladder logic and we're done because it is, but it's important to understand the basics of it because with your Python programs, you're going to be seeing the same thing in the ladders that you're going to see on your processor, so on your, in your software. But basically with ladder logic, hello, if you notice, this is false, this is true, and this is false, which means that's false. And this is C, control relay 1 contact. I make this true, now this is all true, this becomes true, and the whole rung stays true until you turn to stop and make it false, which drops everything out. And you can actually quote-unquote program with lines and lines and lines and lines of this if you want to go back to the 1960s. Now, here we are in modern day. Notice anything different? We've replaced our physical buttons with logical bits that look like contacts, but they're not. This is, I'm trying to remember, I think the proper technical terms like examine on and examine off. But what you'll notice is the way these are named is you have start, local data, let me see here, local 1I data 0, local 1I data 1, which this is mappings to the input outputs of the PLC. So what we'll typically do in like the Python programs that I've been working with is we will actually map this local I data 0 to an alias, which we would call start. And you just basically connect, and then you suddenly have this start bit to manipulate that you can actually start and stop a real machine in real life. But we're going to do way more than just start and stopping machines. So am I keeping everybody, or are we all following along? I tried to make this really easy. Now we're going to get in the second part of machine control and things that you'll see, analog signals. So we're familiar with analog signals, right? I'm giving you one right now. We're doing the whole electronic thing and it's coming over the loudspeakers. But you need to bring this into the world where you're programming, where you're actually dealing with things. And this is where it really gets strong because people want this data and they want to put this data, because one of the main things I work with at Accurate Technology and Test Automation is test systems for the electric submersible pump industry. And what they basically do is they have API and also ISO standards on how to do a performance test on these, and the customers want that information. And if you're just giving it to the customer in a, you know, a spreadsheet or a printout or something like that, they want data that's secure and that is accurate also, so that they need to have that trust, that faith that this thing's actually producing accurate, good data. And the way you get that data is, oh, this is beautiful. So we did ask people know what an analog signal is, right? Okay, from Wikipedia. An analog signal is any continuous signal for which time-varying feature variable of the signal is representation of other time variable varying quantity, i.e. analogous to another varying signal. For example, in an analog audio signal, the instantaneous voltage of the signal varies continuously with the pressure of the sound waves. I didn't understand any of that. Basically. So here's in my brain the way I understand it, the way I always explain it is, in short, an analog signal is an electrical signal, typically from a transducer. So now we threw another word in there, transducer, which I think we have a gentleman over here that knows exactly what a transducer is. He's giving me this knowing look. And a transducer is an electronic device that changes something from the real world into an analog signal. So we're still not in the computer yet, but we're still in the real world, and now we're into an electronic signal, which a transducer, though, can be a microphone, an accelerometer. Has anybody ever heard of an accelerometer? There we go, got a few accelerometer people, which basically it's a microphone, only you put it on a machine and it reads vibration, which vibration analysis is a whole nother fun thing that you can do with fast Fourier transformers and everything else in Python, which I'm still looking forward to the day I get to play with that. Temperature sensors, pressure sensors, torque sensors, kilowatt transducers. This is another fun one. Anybody know what a kilowatt transducer is? No? Basically, it's power, which is kilowatts, equals current times electromotive force, or P equals I times E, pi. That's Ohm's law. It's electronic stuff, but here's the thing is there's a good chance, and I can tell you in my business, I have to read kilowatt transducers, I have to read volts, amps, torques. It's just a lot of fun stuff, love it. And many more. Any questions, any thoughts? Because I move fast, I talk fast. I've been told Yankees talk fast because I'm from Indiana originally. No thoughts, question. We're doing a pause here just to make sure. So if you see this graph, this is basically a representation of your y-axis is amplitude and your x-axis is over time. And this is something you typically see out of your, if you were to hook an instrument to like an oscilloscope or something up to your AC outlet, this is what you'd see. So here's another one. This is a graph of an analog signal. There's a difference, isn't there? This is direct current. This is common to see in 4 to 20 milliamp transducers and things like that, which is also data that you need to come in. So you can have a system that can have this, hello. Hi, how you doing? The microphone's working. And this, which is also an analog signal, and this is usually the ugly beast that we don't like. And sometimes your vibration signals look like this, your audio signals look like this. But this, I just generated some noise and took a snapshot of it. And here's what's really fun is you will see this on top of either of these two. So instead of having this nice clean little line, you'll see fuzz over the whole thing, which is trash that you just don't want. And you can do post-digital signal processing once you get into the computer to help typically oversample an average to clean that up and clean that out of there, because it's definitely nothing of interest. And here we go. How do we get these into the world where Python lives? Okay, we got at least 2 people in here. I know how we get it in there. How do we get those analog signals into where we can actually manipulate it and work with it, save it, put it into the database? Analog to digital conversion. Does anybody here even know how analog to digital conversion works? Kind of. So we're going to go back here and we're going to look at this signal again. So basically what analog to digital conversion is you have a analog front end running at a certain frequency, which is your scan rate, your data acquisition frequency. I've heard it called a lot of different things. But if you had a scan rate that was exactly the same as this frequency, basically you would pick up a point, you know, here, 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 and here, and then you get this radically deformed square wave looking that's nothing like the signal you actually have. So what we do is we usually have a scan rate that's a minimum of 10 times the signal of interest. So we take a lot of tiny snapshots and we measure the voltage at each one of those snapshots, and then we save that into basically an array that says at this time I took this level of voltage, and then you can reconstruct this waveform in a digital world. So everybody's an expert on analog to digital conversion now, right? But the thing is you are going to actually need to know this, because you need to know what kind of, especially if you're doing digital signal processing, because you can actually, you can go through a fast Fourier transform, and you're going to change that x-axis to, instead of time, it's going to be frequency. So you're just going to see one peak at 60 hertz, which is just going to be a line and say, hey, this is because, like I said before, you'll have the crazy signal with the noise and that, and it's going to be able to break out each one of those and the amplitudes, and you'll have that information saved. Ta-da! Now, we're getting into the fun part. How am I doing on time? I haven't even been timing myself. got another half hour. Well, then I guess I'm going to have to tell stories or something. That's why I said I talk too fast. C'est la vie. Okay. And this is where we get into the real stuff that we're actually dealing with, is the industrial communication. Ethernet IP, which is one of the more popular ones. It uses a common industrial protocol, which is managed by ODVA, which you can look them up at www.odva.org. Now, these are mainly used, I can tell you from the research I've done, is the #1 PLC manufacturer in the US is Allen Bradley, and overseas it's Siemens. So if you're actually getting into industrial automation, you're going to run into, I can't recall what Siemens, how they communicate, but you'll see a lot of different things. And also, if you get into data acquisition, you'll get into National Instruments. So has anybody ever here dealt with National Instruments, worked with them? Make really good quality data acquisition components that just about any signal you can imagine that you can actually grab and pull into the digital world. But they want to sell you National Instruments LabVIEW. So has anybody ever played with LabVIEW? There we go. What do you think of it, sir?
It's been a long time. Yeah, it's okay for visual nature.
Yeah, and that's kind of my feeling too, and especially when you're trying to do the industrial Internet of Things, it's a proprietary, it's owned purely by National Instruments, and there is no international standards holding it. But they have actually they're moving to I've read they're moving to Linux now for both the Mac software, which is the driver for their hardware, and they also have a Linux library that will communicate, or a Python library that will communicate directly with their driver. So, and you know, one of the things I'm working on is a Raspberry Pi to just basically do a real quick and easy, gather the data and serve it. And you know, we can go up to some nice industrial PCs from there. Boy, I didn't do that right at all. Now, a second one, which like I said, we got to go back in time, Modbus RTU and Modbus TCP, which Modbus is a protocol that was developed by Modicon in 1979, which is probably older than a lot of people here. And you'll see this a lot of times, like we use a smart meter when we go back to the kilowatts, volts, and amps, and things like that, that you communicate directly to using our RS-485 Modbus RTU, which I just threw a lot of numbers in there, and I need to remember that. RS-485 is a serial protocol that is a master-slave, which basically you have one master, which is typically the PC, or it could be the PLC that you're communicating with another protocol, and you have multiple slaves, and it's a DB9 connector, which you don't even see those anymore hardly. And they usually have adapters for that. Then you also have the Modbus TCP, which is the same architecture, but it's been ported over to work inside of your standard Ethernet IP packets, or your TCP IP packets. So basically, you end up with a packet, but you have all this information of the Modbus from that packet. So I've actually worked Pi Serial, I believe it is, will do direct raw serial communication. And there is a Python library that's built on Pi Serial that will do the Modbus RTU. And I've also worked with the Modbus TCP, and it's like 3 lines of code. Suddenly you're reading and writing to a Modbus device. So it's pretty simple. Thoughts, questions?
Is that different than I2C?
It is very different than I2C. Yes, very different than I2C. And I2C is normally reserved for your board-to-board devices. And this typically, so we'll talk, and I can't remember what the clock rate of the I2C is, but the Modbus RTU very average is 9600 baud, which I think you can go up to 11.2 or something like that, which is slow by today's standards. And also the network you can't do, you just have to do a multi-drop network, which is really just not very clean in today's world, versus Modbus TCP, which you can use all of the modern switches, routers, and any, just like you would with any Ethernet network that you set up in your industrial machine. So Yeah, I've been really impressed with that, and that's the one I've worked with a lot, and we worked with that with C#, actually, and starting to work with Python. See, I'm slowing down now. Good job, Josie. Now, remember when I showed you a relay earlier? Here's that word again, coil. And you notice coil is 1 bit. So it's 1 little bit in a word. Normally what I've done with programming is I will actually, inside the programmable logic controller, I will actually assign these bits to an array and then pass it through as a 16-bit holding register typically, so I can actually read and write and manipulate this. Now here's another fun thing, is you'll notice that this is the Modbus and what its capabilities are. You have coils and you have registers. And each of these coils and registers has an address that you actually have to call this address up. And you have a slave address, which can be slave 1, 2, 3, 4, or in the Modbus RTU, or in the Modbus TCP, you're using a client-server model, which means that you just call up that IP address, and then you get that information from the registers, and you can normally only pass 16 bits at a time maximum, which proved to be a real challenge with some servo motors I worked with, that the resolution, it actually pushes 64 bits back through, but you have to get that 4 registers at a time. And then you have to take that and you have to piece that back together to decide what the position is, which is just loads of fun, especially with somebody who's a little dyslexic. So get everything tied right. Going back to Ethernet IP, so I'm going to jump around a little bit here. Ethernet IP is a lot nicer because you just call it up by its name. And the Ethernet IP, I've been able to run DINTs, which is 32-bit words, INTs, which is 16-bit words, Boolean, strings. So basically, this is a lot more modern, a lot more powerful than the Ethernet IP, or the Modbus. But you'll run into that too. Anybody heard of CAN bus? I know we've heard of Sky Squared C. There we go, we got a CAN bus aficionado. Anybody here drive a car? Got a few people driving cars here. There's a really good chance that the CAN bus is actually in your car running everything. So they typically call that OBD2, which is a computer that sits there and reads the information off of that CAN bus. But it's also moving to industrial automation, which we actually have a torque cell that I've worked with that uses CAN bus to communicate the speed, torque, and all the other information directly and reading that. I've not worked with CAN bus in Python, but this is something that you might run across, and if you've got any input on it and information, hey, that'd be great. I would love to know more about that, on how it works with Python. But it's maddening because it's coming through in binary words, and you have to sit here and make sure that it's, depending on what the manufacturer felt like, make sure that it's least significant bit first or most significant bit first, and then get things flipped around right so you're actually reading good data when you come through. Another thing that I find really fascinating about CAN bus is its hierarchy-based message priority. So every single instrument or device on the CAN bus network has the same level of, I'm looking for the right word here. Basically, they have the same priority on being able to communicate to everybody else, but the messages have the priority. So basically, they send 4 bits, and I like to say it's like playing rock, scissors. So if everybody says the first one, rock, okay, nobody gets to read the message. If the second one says scissors and everybody else says rock, then that one wins. And the highest priority message is like 4 high bits, which means that this is an emergency. Everybody on the network stop, shut up, and listen. As soon as their packet gets through, then every device gets to go play this rock, scissors thing again. So there's no paper in there, just two. You get to do it 4 times, whoever wins, wins. Now, we've talked about a lot of different industrial protocols here, and there's quite a few more out there. You'll run into Profibus, you'll run into all of these other things, and when it comes to actually writing software to communicate and work with these, sound effects. But when it comes to actually writing software to work with these, you're going to have a driver or a way to communicate with each and every one of these industrial protocols, which is normally very proprietary, well, somewhat proprietary to them. They, like Modicon likes to claim theirs. Siemens, I believe, is the one that claimed Profibus. Alan Bradley just finally said, you know, we're going with this OVAA, what they decided to do. Now what we have is you'll find OPC, Open Platform Communication, which originally was OLE for processor control, which means that or process control, which means it only worked on Windows. Once again, the industry's having trouble catching up to modern world, but they're working on it. Now they have what's called OPC UA, which is Unified Architecture, which actually I found a really nice Node.js program that actually reads and writes, and I found a few libraries in Python that I've not really had a chance to play with. But the idea of OPC is to basically take each and every one of these different protocols and be able to put a driver in front of it, and you can connect to this OPC the same way every time. And it's actually designed for the industrial Internet of Things. What I've read online, lots of people are frustrated by it because it can be a little bit maddening to set up. But it's an attempt to try to bring all of these manufacturers that decided to go all these different directions starting back in the 1960s to bring it into one unified architecture that we can run on Linux, Windows, and you can basically control an entire shop floor from your PC or anywhere else. One of the things I'm particularly working on with all of these is I'm working on designing a control, basically we have what's called a main control enclosure, MCE, which contains the brains, and I'm working on putting those brains in there to where we can connect to it through an Ethernet connection, and we can actually, it will display everything in a web page. Read, write, control, and all of that, so the customers just don't have to worry about writing all this fancy software and everything. It's like, here it is, here's the standard API. If you want to write the software, I'll put it on GitHub for you, because I don't feel the future is necessarily in the old closed world where, you know, Microsoft helped build, and I think Linus Torvalds just helped tear apart. And Richard Stallman, anybody look up him? He's a very fascinating guy. But I don't really feel, because like right now I bought the software to program the Allen Bradley PC for the lower end was like $2,000 some just to step in to be able to start doing that crazy ladder logic programming if you want to do that. They have some free stuff out there for the lower end PLCs. But I really think the future is, and I think the customers are going to want, is they want something they can trust but not have to worry about being locked into the proprietary, because there was a company that I'm trying to fill in the void that left from Midland, Texas. They were called Aquila Automation. That's one of the biggest complaints I heard was they sell the machines are out there, now they try to make their money through constantly pushing new software updates and everything, and the customer's like, the system's working, I don't need your new software updates. They're out of business now. So I'm trying to make this as open as I reasonably can, but if it's inside my box, it's mine. So that's why I'm working on making a standard interface with the box that you can have this free and open and out there. And that actually finishes my slideshow. So do we have any questions, comments, or thoughts? Is everybody's brain still working? Because we just went into a totally strange world here.
So there are frameworks that are integrated with Python, allowing you to use Python. Like you said, a lot of National Instruments has quite a...
Okay. So the question is, there's good frameworks to integrate Python with industrial automation, basically. And pardon me on my nomenclature. Like I said, I'm a jack of all trades, master of a few. But there are a lot of libraries out there that you can basically, like the PySerial, which is designed for just direct dumb serial communication. But I found in my research that Python feels like it's pretty much on par with C# for being able to communicate with this industrial world, basically. And when you come into the National Instruments actually has on their website where they support and point you to this open source project for communicating with their National Instruments DIDAC Max is what they call it. So, and that's where kind of you need to know and understand the machines and what's going on. Let me see here. We're going to do National Instruments for a second here. I think we are. That's ProLink, OPC UA client. Whew. So did that answer the question?
Yeah.
Okay.
Is there support from the organizations that, to have Python thrown at automated industrial automation? It's like you can't point a finger at a company like that and blame them or something.
Yeah, and that's another thing that playing with Python and industrial automation, that's probably an uphill battle. I know I've spoke with one oil company that they were actually working with Python for a lot of the data management, the deep learning, and trying to do the big data stuff that they're wanting to do that with all their test data. But you got to get it up to the cloud first. Got all this stuff on my desktop. I'll find it sooner or later. Okay, any other questions, thoughts? I'm paying attention, I promise. I'm over it. But yeah, a lot of this stuff, like I said, it's the industrial communication in general is a standard that is, ISO or some other international standard that they've actually set up. But when you have National Instruments in particular, they're working on selling their product. They sell you their driver, then they sell you the libraries to connect with their driver so you can start programming in C#. But it looks like they're going more open source in these days. Okay, I see a few people thinking. Yes, sir. Question was, Allen Bradley would sell the driver to communicate with their PLC? And the answer is no, especially with Python. It's a lot of open source stuff, and actually the way to communicate is published. And I've actually looked over that, and it's a lot of hexadecimal that I really don't want to get into. I just trust other people have already done it. And do Google. I'm actually looking at working with, it's called C3PO, which is CPPPO, to work with the Ethernet IP. Now remember, Allen Bradley's not the only one that does Ethernet IP, so being able to actually develop something in your tool belt that you can communicate with Ethernet IP, now it's like, suddenly you have the ability to get into data acquisition and machine control, which use with extreme caution if you get into that part of it. So
the Python is being used to process the data once that data is received in the...
Exactly.
So, because I would imagine Allen Bradley would be real protective of they don't want to give up control of their operating system.
So basically what he's saying is, and correct me if I'm wrong, is Python is, basically Allen Bradley wants to be protective of their operating system. Yes, absolutely, but Allen Bradley also wants to be able to work nicely with everybody else, so when you invest in Allen Bradley, you're investing in something that you can grow with and it is future resistant. So that's why they publish their standards on how to communicate with them directly, and why the people are out there taking Python and actually making classes to communicate directly with those Allen Bradleys. So, and like I'm using, for my HMI, I'm using Red Lion Control, which their configuration software is free for, here we go. I actually bring this one up. Yeah, I'll throw it up there. Ta-da! And this is where we go about designing a, oh man, I can't see it. Web designer programs, and actually the new one actually has OPC UA built in, OPC UA server built in, which you can communicate directly with the, there you go. Then you can draw pictures on it and make the pictures do things by assigning the bits and everything from the network that you connected to, which it'll connect to Allen Bradley, Ethernet IP, and this is all, it's free. And as opposed to if the Modicon, which I actually have a project I'm working on, which is about $1,000 to work by the program to work with their HMIs. So, like I said, it's really hard to try to operate this.
What is that ID right there?
This is actually the Crimson software that works with, so this is actually a product of Red Lion to work with their Red Lion product. And as opposed to forcing you to buy the HMI and the software to program the HMIs, they just force you to buy the HMI and say, here's the software for free. As opposed to Allen Bradley, which they will force you to buy their several level ups of their Studio 5000 suite. So, but that's the beautiful thing here is actually the Crimson 3.0 is they now include an OPC UA server in their HMIs. So if somebody designed a machine that says, hey, I put this HMI on here, I have the OPC UA, here's all of the data that I need to put into database and save and manage and go through or do whatever, then suddenly you just know, point to this IP address, use the OPC UA library and go for it. And I know I'm in changing librarian classes, so you have to excuse me. So any other thoughts, questions? How many minutes do I have left? Close enough? I don't know. Yeah, it's until 12:30, isn't it? We got to do the 15-minute thing, hang out. Are you sure? I'm going to do that tonight. I think they're mobilizing. They're like, Josie, you're done. Well, thank you so much for your time, and I appreciate you coming to listen to, get a little bit of education on industrial controls and how you can program, do cool things with them.